Okay, so let's start with the lecture. Welcome. It's almost the end of the term now, and so this is one of the last lectures. And today we'll hear something about sponges or sponge functions, so cryptographic sponge functions, and stream ciphers, which is something we didn't yet cover here in this course. Okay, so let's start first with a small outline. So contrary to the title, which is sponges and stream ciphers, we will first start with stream ciphers, and we'll hear something about the stream cipher model. So what actually is a stream cipher and how is it different from a block cipher? Then we will talk about some basics of stream ciphers, so what basic terminologies, then of LFSRs and NLFSR. So we'll talk about it later, what this means. And finally, we'll also give some stream cipher examples. And then towards the end of this lecture, we will hear something about sponges or cryptographic sponges. So this will be the smaller part today, but still, and it should also maybe help to prepare you for the task, also for the practicals. Okay, so let's start. And in case you have any questions, just ask them. I have the YouTube chat here on my other monitor, so I can see the questions. And I think the delay is approximately 5 seconds. Okay, so let's start with the stream cipher model. So what actually is a stream cipher? And we can start by naming this Vernon scheme and this one-time pad. So I'm sure that most of you have heard about this one-time pad. And this is something which has perfect secrecy. So it's not possible to break. It has all the entropy, so to say. But the problem about this one-time pad is, of course, that we use it only once, and that we need it to be as long as the plaintext we want to encrypt. So for example, if we have a plaintext of 4,000 bits, we also need this one-time pad to be a size of 4,000 bits. But of course, this works very well, so it provides perfect secrecy. And what we do is we add this very, very long key, which is as long as the plaintext, to the plaintext. So this is a simple XOR operation, and we then basically have a ciphertext. And we can send this ciphertext to someone else, and if the other person has the same key, then they can add the key again to the ciphertext, and what they receive is the original plaintext. So this is very good, very strong, in fact, but we need the key to be quite long as the plaintext. So that's essentially the problem of this scheme. And a stream cipher basically tries to do something very similar, but tries to avoid this problem of having a very, very large key. Because of course we also would need to transfer this large key securely to another party. So this is also a problem. So what we can do is we can think about this problem differently. We can try to generate a pseudo-random key stream. So this is not really random. This is not something we choose as being random, but it's pseudo-random. So we can basically try to generate a very long pseudo-random key stream from a seed. And maybe some of you have already heard about this term seed. And in this case, in the case of a stream cipher, it's a real key. And usually we can build a stream cipher such that this real key is much shorter than the key stream we want to produce. So what this means is that we basically have a very short key, which generates a very long pseudo-random key stream. And this very long key stream can then be added to a long message, for example. So the only thing we need to transfer to another party, and the only thing we need to keep secret, ideally, is this very short key. So this is the basic idea of a stream cipher. And yeah, this is also different from a block cipher, because in a block cipher, so you can actually use block ciphers to build stream ciphers, but here we talk about something which is added bit by bit. So this is different from a block cipher, which operates in blocks which are, for example, 128 bits. Okay, so and for security, of course, if we have this very, very short key, which creates this long key stream, for security, of course, we need to eliminate any shortcuts to finding this very, very short key. Very short, it's also 128 bits, for instance, so not so short, but it's much shorter than the key stream. And of course, we need to basically eliminate any possibility to find this key if we are given, for example, the patterns of the longer stream. And the nice thing about the stream cipher is actually also that it is very, very efficient on hardware. Okay, so how does this look like? So this is now so that the graphic is essentially similar to this Vernam scheme before, but instead of adding a very long key now, we have this finite state machine here. And yeah, here are 3 different keys, but you can also think about a single one of them. So essentially what we do is we apply some short key. We then have this finite state machine, which essentially produces the key stream. And this key stream is then added to the plaintext. We can then send the ciphertext to someone, and basically another person can use the same keys in order to basically bring the state machine to the same state. And then essentially the same key stream is produced, which, when we add it back to the ciphertext, results in the final in the initial plaintext. So this is the basic principle of a stream cipher, basically to make this whole one-time pad more efficient. Of course, it's not perfectly, so it doesn't provide perfect secrecy anymore, of course, but yeah, that's the idea of the stream cipher. So are there any questions to this for now? Okay, then let's continue. However, and this is the problem with all of these constructions here, if we use essentially the same key stream to encrypt 2 different messages, then what we have is that, for example, the first ciphertext is the first plaintext plus this key stream, and the second ciphertext is the second plaintext plus the same key stream. But what we have is this relation here, which means that if we know, for example, one of the plaintexts, we can basically derive the other. And also the statistical information coming from this relation can be or maybe enough to decrypt it. So what we don't want to do is basically use the same key for 2 different encryptions, or the same key stream, sorry, for 2 different encryptions. And this can be avoided, and maybe you've already heard about this term, about an IV. So it can be avoided by an IV, by an initial value. And the idea is that we not only use the key, the single key, which we don't change between the 2 encryptions, but we also use some public, so usually it's public, we also use some public IV value, which basically is different in these 2 encryptions. And this results in a different key stream, but the short key still remains the same, and we cannot set up this relation here. So this is basically what is avoided here. And if you remember, this is also something which is done in many block cipher modes. So this initial value thing. So it's essentially the same idea also here. And it's not a problem for basically transporting something secret, because it does not need to be secret usually. So this is the advantage. Okay, so this is a stream cipher. So this is, of course, on a very abstract level. We didn't talk about how this internally works, and we'll only talk about briefly about that today on a high level. But yeah, in a sense, this is a stream cipher. So what we need from a stream cipher, for this key stream, so to say, is that we need essentially an efficient generation. So that we need basically that the key stream is fast, because usually we do something in the beginning which is called initialization phase, where we basically have operations with the actual key. But after that, we want to generate a key stream. This needs to be efficient. So this is the idea. Of course, the key stream also needs to look random, at least, and be unpredictable. So it needs to have a large period and nonlinear also. And we'll talk specifically about the period later. And yeah, it should also be secure in the sense that basically there's a very low correlation between the actual key stream which is generated and the key which was used to generate the key stream. So again, the key stream is not chosen by the user, so only the key is chosen. The key stream is generated basically by the key deterministically. Okay, so I've talked about LFSR before. So this is essentially an abbreviation. It's for linear feedback shift registers. And this is a basic component of some stream ciphers, not of all of them, and it can be used to build something, so to basically generate a pseudorandom sequence. And as it's a basic component of some stream ciphers, we will briefly talk about this LFSR, so what this actually is. Okay, so what is an LFSR? And we only work mod 2 in this section here because it's not necessary to work with something different. And basically what we have is now that we have a shift register. I will have a sketch then later. It's a shift register whose next input bit is basically a linear function of the current state, of the previous state. And this LFSR construction has been a workhorse for military encryption for as long as electronics basically has existed, because it was very fast, and also it was already used, for instance, in the military. And yeah, it's very fast. It can be, so it's usually slow on software. So that's the properties of that. And how does that look like? So for example, this is called a Fibonacci LFSR or a Fibonacci representation. We will then later talk about the Galois representation, which is maybe a bit easier to understand how it works, but in a sense, so you don't need to know the precise names, but in a sense, so they're somewhat equivalent, the Fibonacci to the Galois, so they can be transformed into each other, and they also have the same properties, but it's just basically a different representation. Okay, but let us look at that now. And usually, if you write down, if you see a construction of an LFSR, you have the output bit here and the next input bit essentially here. And what happens? So this is the state. This is some bits essentially. So this is either 1 or 0. This is either 1 or 0, and so on. And what happens now in one step, so to say, is that we basically compute the next input bit here using this state here. And how this works is essentially that we basically have the sum of these bits of the previous state, but by constants here. And of course, some of these constants here may be 0. What this means is that, for example, we have the sum of only an example, we have the sum of only this bit and this bit, which would mean that essentially this constant, this one, and also this one is 0. So yeah, and usually this is not 0, but we will see later how this actually works. And given such a construction, we can now write basically down this equation here, which computes us the new input bit, which enters here, given these constants here and given the previous state. And after we have done this, so this is basically the one step, so to say. After we have done this, we generate the output stream, and the first bit of the output stream, is xn. So this is the first output bit, and this is then the second output bit, and so on. And we can basically just rotate this and generate many output bits infinitely. And the question is of these LFSR that so this has a period, the output bits have a period, and they have to repeat somewhere after some steps, right? So that it cannot be basically completely pseudo-random for forever. And we'll see later how this is related actually to the period. But for now, just see this construction, and essentially we have a state. The next input bit is a linear function of this previous state, and these are the output bits, so the output stream. There's no key here yet. Okay. So for example, maybe to illustrate it more, we have some constants here being 0, which means in the previous example we have C1, C2, and C4 0. So basically C1, C2, C4 0, for example, and we have only the sum of these two bits here, C3 and C5, since these are 1. And what this results in is basically that the next input bit is the sum of xn plus xn plus 2. And these are precisely xn and xn plus 2. Mod 2, of course, so essentially this is an XOR operation. And if we now have some initial state, so for instance 0, 1, 0, 0, 0, so this will be basically 0, 1, 0, 0, 0, the initial state, we can, based on these bits, we can essentially generate the new bits. And then we use these 5 bits, we shift one, use the next 5 bits, and so on. And basically we generate such a sequence. And in that case, so for that LFSR, this sequence repeats after 31 times. But this is of course not always the same. And this is also closely related to the length of the LFSR and to the coefficients which are to which coefficients are 0 and which are 1. Okay, so if we have this linear function now, which basically generates bits infinitely, then we can have 2 settings. The first setting is that the starting sequence, so essentially the starting state, is secret, while the constants are not secret, so they are public, and these are these C's. And the second setting is, for example, that the starting sequence is secret, but also the constants are secret, so all of it, essentially. And now we can essentially distinguish between these 2 cases. And well, first we have some good properties, of course. So the linear feedback shift register passes many pseudo-randomness tests. So essentially it's for generating a pseudo-random sequence of bits. And the maximum period, again, we will talk about this later, is 2 to the L-1. So what does this mean? Here the length is 5, essentially, because we have 5 such state bits. And 2 to the power of 5 is 32, minus 1 is 31. So in the previous case, we actually reached the maximum period. And what are some bad properties? Well, if the constants are public, then any output sequence of length L recovers the initial state and also all future outputs. Why does this work? Well, if we have the public constants and if we have exactly 5 output bits, so subsequent output bits, then of course we can generate all future output bits by just applying the linear function, but we can also go back, of course, by just reordering the equation. So this may be bad. Another bad property is that if also the constants are secret, then if we use only one LFSR directly as a keystream generator or pseudo-random bits generator, then we can also attack that. And this is done with an algorithm which is called the Belkamp-Massey algorithm. And yeah, if you want more information, it's here. We will not talk about this algorithm today. And this is also a bad property. Of course, this LFSR is not unpredictable. What does this mean? Well, if we have a state given, then of course we know what comes next. So because we just apply the equation. Okay, so now there's basically a difference between random numbers, pseudo-random numbers, and basically unpredictable. This notion of unpredictability. So for a random number, so this is really purely random. We cannot say what the number will be, and it's also not generated by any deterministic process. And for a pseudo-random number, this is, maybe we can say, an approximation of a random number, and this is exactly what happens here actually. And this is useful, for example, for some simulation purposes, or if we need some cheap pseudo-random numbers for some purpose, but this alone is usually not sufficient for security, which doesn't mean that pseudo-random numbers are never actually used in cryptography. So there are actually use cases for pseudo-random numbers, but in this case, it's not alone for security. And then, stronger, there's this notion of unpredictability, of course, which this LFSR, due to the problem mentioned earlier, does not fulfill, because we basically, given some sequence, we cannot predict the next bit. So we can predict the next bit, hence it's not unpredictable. Okay, so we've talked about this period thing before. So in the case of this 5-bit LFSR, we had that essentially the maximum period of 31 is reached, and this is actually the maximum bit of any, so 2 to the power of L minus 1 is the maximum period of any length L LFSR. But the question is, what is the real period? So if we just choose these constants here in some random way, so I don't know, this is 0, this is 0, and this is 1, and some in between are 1 and 0 randomly. So the question is, what is the real period of the resulting LFSR? So when do the bits start to repeat? And we need some, so not so much, but some math background for that. And here I want to start with the power series. So basically a formal power series is defined by this way here, and we have some properties, of course. So if, for example, two power series are the same if the coefficients here are the same, so every coefficient is the same. Then we have the addition of two power series, which basically so of A and B, which basically is the same as having new power series with coefficient C, which is the addition of these two corresponding coefficients. And what we can also have is the product of two power series, and this is something you may be familiar with if you basically, for example, multiply two polynomials, for example. Then we have a different rule, which is that one, basically that the single coefficient of the new power series is a sum of products of the previous coefficients. So this is very basic still. And yeah, an example, I'm not going through this example now, but I can verify that this is true. But what really want to go at is polynomials. And essentially a polynomial is a power series with a finite number of non-zero coefficients. So for example, so we will have some examples later of polynomials, yeah. And we should have some properties for such a polynomial. So for example, we have a degree property, and we say that the degree is d, for example, if the coefficient at x to the power of d is not 0, so if it's something which is non-zero, then we have x to the power of j. But we also want for this property here, for the degree being d, that every coefficient for larger d, so x to the power of d plus 1, for example, is 0. So then we have a polynomial of degree d. So the leading coefficient is gives essentially the degree of the polynomial. So this is only a property of a polynomial. And now we come back to our LFSR. We try to connect this polynomial somehow with our LFSR. And now note that we have a slightly different graphic here. So we don't have this Fibonacci LFSR anymore, but instead we have this Galois LFSR. So again, they are equivalent. So one can be transformed into the other, and also the properties are the same. It's just a different way to basically represent the LFSR. And I've chosen to use this one here for this period stuff, because essentially I think it's maybe a bit easier to understand why this actually works. Okay, but back to this LFSR. So in this presentation here, and so usually it can be denoted by L and CD, where essentially L is the length of the LFSR. So in the previous case, for the previous example, we had 5L. And CD is a so-called connection polynomial. And what this connection polynomial does is it essentially describes us which of these coefficients here are 0 and which are not 0. So remember that we work mod 2 here, so we only have 0 or 1. We don't have any other values for these C's here. And if we are given such a Galois LFSR, we can essentially translate it to the connection polynomial d. So big D, it doesn't really matter what this large d is. It can also, so in the literature you will also find x, so small x or large x in many cases. So this doesn't really matter. But essentially we have large d to the power of L plus some coefficient, so this one here in that case, times d to the power of L minus 1, and so on, plus C1 times d, which is essentially for this coefficient here, plus 1. So you may note now that that there's no coefficient in front of the d to the power of L, and also no coefficient in front. So essentially, no, the coefficient here and here is always 1, so to say. So, but we don't take its variable. So this is basically constant 1 here, and also this plus 1 is always there. is also a 1. Because this is essentially the coefficient 1 times d to the power of 0, which is 1. And we'll see later, or I can mention later why this always has to be there, at least for good LFSR, and also that one. But I think we will see it later. And what happens in the middle is basically variable. So this depends on the length L, and yeah, so essentially these coefficients depend on length L, but these two should always be 1. Okay, so this is the Galois presentation. It's a bit similar a bit different to the LFSR to the Fibonacci representation. Sorry, but again we have this state essentially. In that case, S1 to SL. I hope the indexing is correct, but it should be. And essentially the working is the same. We have the new input bit here, and what we produce here are the output bits. So that works the same. But you can note, for example, that the arrows go in different directions if you compare it with the representation above. But it's essentially the same. Okay, any questions to that? Because I think yeah. So I know that this is still very abstract, and it doesn't really make clear why we actually need this, but hopefully it will be more clear later. So let's have an example, for instance. So what we do here, essentially, we define a Galois LFSR, but we say that, well, the Galois LFSR is denoted by this L and the connection polynomial, and the connection polynomial essentially gives the constant values here, so if they're 0 or if they're 1. And now, in order to be more concrete, we can, for example, say L equals to 4, so we have 4 state bits here, and we can say that this is 1, and so this means essentially that we are at the third position, so we set the third constant to 1, so we have 1 times d to the power of 3, and here in front we essentially have 0 times d to the power of 1 plus 0 times d to the power of 2. Okay, so that's essentially the conversion from this connection polynomial to this Galois LFSR. And as said before, we always have this constant 1 here, and we always have this constant 1 also for d to the power of 4. This is due to the period also. Okay, so we have this connection polynomial, and yeah, this was actually the example. So just a translation here. Okay, but now this doesn't yet explain why we need. Which properties, for example, this connection polynomial has to fulfill in order to guarantee that the LFSR generates a maximum period output. And in order to give these properties, I have 2 slides here. First about irreducible polynomials, and then about primitive polynomials. But first about the irreducible one, we say that the polynomial, and this is in that case the polynomial here, the connection polynomial. And again, the d doesn't matter, so sometimes we will find it with x also, it's the same. And we'll say that such a polynomial here is irreducible if essentially it cannot be factored into products of 2 non-constant lower degree polynomials. And in other words, what this means is that a polynomial f of x is irreducible if it doesn't equal to g of x times h of x for any g and h which have a degree larger than or equal to 1 and smaller than basically m minus 1, if the degree of f of x is m. So essentially, I cannot find 2 polynomials which have a smaller degree except the non-constant polynomials, so except, for instance, the polynomial just 1. And I cannot find 2 lower degree polynomials which, if I multiply them, result in f of x. And if this is the case, if I can't find them, if they don't exist, then f of x is said to be irreducible. And this is also part of the definition. So if we have f of x irreducible, then f of x is not 0. So it's a concrete polynomial. Okay, so let's continue with the second definition. This is maybe a bit more abstract, and I guess you just have to trust me on that one. So besides a polynomial being irreducible, it can also be primitive. And the condition is that it is both irreducible and it has a polynomial order. So this is called polynomial order of 2 to the power of m minus 1. And m is the degree of the polynomial we are talking about. And what polynomial order means that basically it's the smallest integer, it's the smallest exponent, e, for which the polynomial we are talking about divides x to the power of e plus 1. So for example, if we have some polynomial x to the power of 2 plus x plus 1, then we can find out the polynomial order is 3, since it doesn't divide x to the power of 1 plus 1. It also doesn't divide x to the power of 2 plus 1, but it does divide x to the power of 3 plus 1. So this is essentially the definition, and that's called polynomial order. And this is actually what is important what is very important for the period to the maximum. So these two properties and essentially this polynomial order here. And so basically a polynomial needs to be primitive. And we will intuitively see later why this is actually the case. Any questions on this? Okay, then let's move on. So these are just some examples. We have that this polynomial, for instance, is irreducible and also primitive. And we also have that this polynomial is irreducible and primitive. And this is just on a side note here. This polynomial here, x to the power of 4 plus x to the power of 3 plus 1 is exactly the one we used here. So essentially we now know that the period of this Galois LFSR will be maximum. So 2 to the power of 4 minus 1, which is 15. And what is also interesting, maybe as a side note, is that these two polynomials are actually very, very similar in that, if I'm not mistaken now, this one is essentially the Fibonacci LFSR representation of that one. And basically both of course generate maximum period LFSRs. Okay, so these two polynomials, but then we have also this one, for example, so x to the power of 4 and so on plus 1, and this is irreducible, but this is not primitive, because x to the power of, because it basically divides x to the power of 5. And thus the period of this polynomial, so it has order 5, and not this one as a primitive polynomial has, because this would be the order of a primitive polynomial. Okay, so again, period of LFSR, if the connection polynomial, so if the polynomial which defines this LFSR is a primitive polynomial, then what this means is that each of the 2 to the power of L minus 1 non-zero initial states produces the output sequence with a maximum period, the maximum possible period, which is actually 2 to the power of L minus 1. And in other words, each of the possible non-zero states is actually produced. And if you start with a 0 state, then you will quickly see, both with the Fibonacci representation but also with the Galois representation, then essentially you will only produce zeros. So this wouldn't work. So you need to start with a non-zero state, and then essentially, if the connection polynomial is primitive, you generate each of the 2 to the power of L minus 1 possible non-zero states. And we will see in a minute why this, so intuitively why this works. However, if this connection polynomial is not primitive, but at least irreducible, then essentially what we have is that each of the states we can use as an initial state produces the sequence which with a period which is basically equal to the least positive integer n, such that the connection polynomial divides this n plus d to the power of n. And this is exactly this polynomial order definition. Okay? So what we try, of course, is to have a connection polynomial which is primitive. And this is actually possible for every size. So it's not really a problem choosing a polynomial which is primitive. So they exist for any size. Okay, some examples again. So we know that this polynomial is primitive. We already had it before. So we also know that if we generate an LFSR using this polynomial, and this is actually the LFSR we generated before, then we know that the period will be 2 to the power of 4 minus 1, which is 15, which is maximum. However, since this is not irreducible and it divides 1 plus d to the power of 1, the period is only 5, which is much lower than the maximum possible period, of course. And yeah, we can also see it with this example here. Essentially what we try to do is we try to have a primitive polynomial here. But the question is, of course, why does this work? So there is a very intuitive explanation. I think it's much easier to see with the Galois LFSR, so we can think about it, what this operation actually does. So what we do is, if we basically generate the next output bit, is that we essentially do a shift operation. And this shift operation is, in these polynomial terms, a multiplication by d. And you can also think about it in software. For example, if you have some bit value and you shift it to the left, then what you essentially do is you multiply it by 2. And so this is in the basis 2. If we have the indeterminate d here, basically what we do is, in this polynomial representation, that we multiply by d. Okay, so this is the first operation we do, we multiply by d. And then if this output bit is 1, we can think about what happens. Well, if it is 1, then it essentially goes to each position here where we actually have a coefficient which also equals to 1. And essentially all the bits at these tab positions flip because we add 1 here. Okay, and the new input, so it basically goes here unchanged. The new input is also 1. So what we do, basically we shift 1 to this side here, and we add 1 to each of these positions of the connection polynomial, and the new bit essentially which gets shifted in is then also 1. So what we can also say is that we basically shift to this side, and then we add the connection polynomial to the state. Or more precisely, we add each of the constants where it's 1 in the position of the connection polynomial to the current state. So this happens when the new output bit is 1. However, if it's not 1, it can already be 0, and if it's 0, then essentially nothing happens here. Nothing gets added. It doesn't depend on the coefficients here. Basically, either it doesn't get added or 0 gets added, so nothing changes here. And also nothing changes here either. Because essentially we shift 1 to the side and we add 0 here, so basically the new input bit becomes 0. So nothing happens except that we shift everything to the side. And if you think about a bit value, for instance, in software, then if you shift to the side and if you do nothing else, then you only multiply. So nothing else happens, of course, provided that you don't shift outside of the word size and so on. So what this is, in a sense, is a multiplication by d plus the potential reduction if it escapes the field. So if it essentially escapes the room of this connection polynomial. And if you compare this with, for example, of multiplication between two polynomials in finite fields, and with the reduction of an irreducible polynomial in that finite field, then you will see that for the bitwise methods, this is exactly what happens. So this is exactly what happens. So essentially we multiply by d, and if we basically are outside of the field, we reduce again. So what this means is that in each step we multiply by d, so we basically, what we compute is, we compute successive powers of d. And now it makes sense that if the primitive is actually, so if the connection polynomial is primitive, it can generate those successive powers, and indeed all the to the power of L minus 1 non-zero elements are generated. So that's the connection between this representation here, or the connection polynomial, and actually the possibility to generate all 2 to the power of L minus 1 different elements which are possible. And of course, if this state is 0, then I can only generate zeros. So I also need to start with some non-zero state. Okay. Then let's lastly talk about the linear complexity of an LFSR, or of a sequence. So if we have some sequence of bits now, which is generated by some LFSR, and if the sequence is very long, for example, infinitely long, then the linear complexity is essentially the length of the shortest LFSR that generates exactly the sequence, or it's infinite if there's no finite LFSR which can generate the sequence. And if we now have an infinitely long sequence which essentially consists of smaller sequences which are the same, then the linear complexity of this is essentially the linear complexity of this infinite sequence, so of the smaller ones here in that case. And again, so if we have a sum output bits, then we can actually recover the LFSR using this Bellekamp-Massey algorithm, which is not part of the lecture. Okay, this is just the property essentially that if we have two sequences, so different sequences of bits, and now we consider a new sequence where we basically just add these two sequences, so make an XOR sum, one over the other, then essentially we don't, we essentially have the linear complexity of both is at most the linear complexity of the one plus the linear complexity of the second sequence. And what we try to do, of course, for cryptographic applications is that we try to have a very large linear complexity. But in general, this is not sufficient. So we try to have something more than that. Okay, so this was only LFSRs, and if we use only LFSRs, it's in general not very secure, so we usually need something more than that. And this is now very short. This is about nonlinear feedback shift registers and clock control generators, which are essentially also that. Okay, so the problem is always this Bellekamp-Massey algorithm. So the possible solution would be, instead of a linear combination of bits, to have a nonlinear combination or some nonlinear filtering. And this is what is actually used in stream ciphers, which are based on LFSRs. So for instance these, but there are also others, for example grain, which is more recent. Okay, so what is a nonlinear combination? So for example, we have two LFSRs here, and we have some, so this generates linear combinations of bits. So this is, again, the Fibonacci representation. So this is one LFSR, this is a second LFSR, which also generates a linear, linear bits, essentially. But then if we combine these two different LFSRs with a function which is nonlinear, then what we have is also a sequence of bits, but a nonlinear sequence of bits. So for example, this can be an AND, very in simple terms, an AND operation. And what we could also do is something more complex, but essentially the same effect. So we could use three LFSRs, where one is essentially used to decide which of these two LFSRs is chosen or for the next bit. And this is the circuit, and essentially the output here, essentially, so this the clock here decides of the LFSR which of these one is chosen, and then essentially this is the output. So the new output is the sum of the new output and the old one. And yeah, this is another way of increasing essentially the complexity of the final sequence. But this is, yeah, just so. Okay, and some real-world examples maybe of stream ciphers. So which stream ciphers actually are there? So first, a very, very famous one, which is Tritium. It's from 2006. And it has three components. So now we see actually the components from before. We have an 80-bit key. So there's also a 128-bit variant, but we'll not talk about that. And we have this 80-bit IV, so this initialization value, and also a 288-bit state. So you see that now the state is much larger than in our previous examples. And the interesting thing here is that no LFSRs, at least not in their basic form, are included, but essentially it uses different N LFSRs, so nonlinear feedback shift registers. And all operations are in modulo 2, so with these XORs, for example. And Trivium is actually very, very efficient on hardware. And yeah, so that there exists an attack that breaks some initialization rounds. So what we usually do, for example, in a block cipher, if we talk about attacks, we try to talk about, for example, about the attack which breaks 8 out of 10 rounds. But in stream ciphers, of course, it's a bit different because we don't have rounds, such as in block ciphers. So what we usually do when we talk about, so to say, round-reduced versions of stream ciphers, we attack a smaller number of initialization rounds, because these initialization rounds in a stream cipher are usually there to provide the security, so to provide confusion and diffusion and all of that. And then the key stream generation is after that, which is very fast. So in order to attack a round-reduced variant of a stream cipher, so for example Trivium, we can try to attack a limited number of these initialization rounds. So this is a bit different from the concept of block ciphers. But this is just a side note, it's not part of that here. And yeah. Okay, so how does Trivium work? We have an initial state, which essentially consists of these key bits and the IV, so the initialization values, and this very, very long vector of zeros and some ones. And then we have this setup, which essentially does this sometimes, so over 1000 times. And you see here already that this is not linear anymore. This is non-linear because we essentially not only have the addition of state bits, but we also have the multiplication here, or the AND function in hardware, or in F2 of state bits. So this is non-linear. And okay, so we do this over 1000 times, and after, so these are these initialization times. And after we have done this, essentially we can generate the key stream. And this is this operation here, where essentially the key stream consists of Z1, Z2, Z3, and so on. And these are these ZIs here, which are generated. And this is actually now very, very fast. So faster than the initialization. So first we initialize and then we keep generating the key stream. And this is the state update function, which is the same as here in the initialization step. Okay, so of course you don't have to remember how this works. It will not be part of the exam to write down all operations precisely of the Trivium stream cipher, but it's just to give you an idea of how this precisely, or how this concretely looks, and yeah, go away maybe a bit from this abstract level. All right, okay, there are also other stream ciphers, of course, for instance, Cha-Cha, which is based on Salsa, with a slightly different round function. And here we have a much larger state, or double approximately than double as Trivium. And what we do is essentially this operation here, which is called a quarter round operation in the context of this cipher. And essentially we apply this sequentially, and the output is then also used as the key stream. And this whole construction here, as you can see, for instance, this plus here, this is actually quite fast in software. This is not so fast in hardware because we would have some carry bits here, but in software we don't care about them. It's fast nevertheless. So it's basically the instruction here. So this has been built for software implementations, and indeed with 20 rounds this Cha-Cha is used in the TLS, for example. So this is another type of a modern stream cipher. Of course there are many other designs, and most prominently stream ciphers are used in telecommunications. So for example in the old GSM, also in Bluetooth and in UMTS 3G. So these are, for example, Snow2G, Salsa, and Cha-Cha. These are software oriented. And there also was this eStream project of eCrypt, and as a result of that project, basically also new stream ciphers emerged. And one of them was this Trivium we've talked about before, but also Grain, which is quite important, and there also exist different versions of Grain. And one part of Grain is actually an LFSR, so it's one component of Grain. And there are also some number theoretic constructions based on hard problems, which we don't talk about here now. Okay, so a short summary. So what is the core idea of a stream cipher? The core idea is to essentially expand a short key, which we can easily transfer to someone else, into a longer key stream, which we then add to the plaintext or to the ciphertext in order to basically decrypt. And yeah, so this is the main idea of a stream cipher. And there are many LFSR-based stream ciphers. This is so LFSR is a very simple mathematical structure, and but it cannot be used alone. So it needs some nonlinear combinations also for security. But for example, in A51, which was used in GSM and also in Grain, so an LFSR is part of the components. And yeah, there are also many other variants of stream ciphers which do not use LFSRs. So for example, Trivium. And yeah, one alternative, so maybe this is also something interesting, and we didn't talk about that so far. So there's also an alternative to building a stream cipher with these LFSR approaches. Namely, we can just use a block cipher in counter mode. Because what you essentially do with a block cipher in the counter mode is that you generate a very long key stream, and this key stream, which is essentially generated from a single key, this key stream is then also added to a plaintext, for example, or to a ciphertext in order to decrypt. So this is essentially a stream cipher which is built using a mode, the counter mode, together with some block cipher. Okay, are there any questions to that? So this was essentially the larger part of today's lecture. Okay, then let's move on with a quick introduction into sponge functions. Yeah, so cryptographic sponge functions. And first a bit about the motivation. So we heard about stream ciphers right before that, and we know that with a stream cipher we can generate a very long key stream, an arbitrary long key stream, and we can just add it to some plaintext and we receive a ciphertext. The problem is, if we do this with a block cipher, it's not so easy, because a block cipher maps a fixed size input to a fixed size output, and the sizes they have to be the same, otherwise it wouldn't be a permutation. And this mapping, so from this fixed size input to the fixed size output, this mapping is actually secret, and it's fixed or defined by the key. Okay, so this is a block cipher in simple terms. And what this block cipher can do is it can encrypt a single block, of course. So what about more data? What about if we want to encrypt 2 blocks or 1.5 blocks or something like that? So this is one question. The second question is, what if we don't only want to encrypt something, but what if we also want to authenticate something or to provide also integrity? And now if we want to do this, we usually have to do something different. So for example, use a CDC mode or a counter. So this doesn't provide authentication, but it's for the more data part of the problem. And also for authentication, then we need to use different things or modes together with this block cipher. So this may be a problem. So this is part of the motivation. And now if we have some scenario where we want to do it, so authentication, encryption, and with more data, then it's sometimes not very clear which mode we actually want to use. So do we want to use counter mode, but then we would need something for authentication, and so on. So this is not always so clear. And there's also another problem. Maybe this is more of a semantic problem, but it's still maybe philosophical, but it does make sense. The thing is that for these modes, so for example in the counter mode, we always use the key for each block. But the key is actually secret, and we want to protect the secret, but we always use it. So it's always needed and used. So this intuitively, it's not very good. And yeah, we heard about stream ciphers before, and this solves the more data problem. but yeah, there are also other problems with stream ciphers. Some of them are not very easy to analyze, also when it comes to the maximum period actually. And the question is there a more generic approach, which is maybe easier to analyze and easier to build and easier to adapt, and which is maybe somewhat similar to stream ciphers. No, not exactly the same, but similar in the sense that we can actually use it to encrypt, for example, more data. Okay, so that's the general motivation here. And ideally, we would need, or we would like to have something which essentially doesn't use the key always. So this would be very nice. And so yeah, So first, we can start about a keyless permutation. So I've talked about the block cipher. Block cipher uses a key. So now I've told you that we don't actually want to use the key always. So let's try to just take the key away, which makes the block cipher essentially a fixed permutation. So it has no key. And now let's assume, for the sake of the explanation here, that the resulting permutation with a known key or without a key and just constants, let us assume that it has no non-random properties, at least no clear non-random properties. So for example, it has no distinguishers, so it's not easy to distinguish that from a random permutation. This is great because we don't deal with the key anymore, so we have no problems here. But a single permutation alone is rather useless. So first, we don't solve this more data problem, and secondly, we still don't have a key, so it's not very secure. So it's all public, right? But let us just assume we have this perfect permutation which doesn't use a key, but which has no visible non-random properties. So very good permutation, which is secure, so there are no distinguishers. So let us just assume we have this permutation. Now the question is, how do we use this? And this actually brings me to the sponge function. So remember from the previous slide, this permutation is this calligraphic P here. And now let's say that actually this P, so this is one permutation call, and this is also a permutation call, this is also a permutation call, and so on. And this is some initial value here, this calligraphic I. And let us say, for the sake of the example, that this value is actually all zeros. Okay, it contains all, so the all zeros value. And now let's say that, for example, we have two branches. We split this all zeros value in two parts. Okay, we'll see this later. But essentially what we do is we add some message parts here before the permutation call, and ignore for now that we have here a branch and here a branch. Just see the fact that we add one message part here between the all zeros thing and the permutation call. So essentially we start with the input being the message, the M1, so the first part. And then we apply the permutation, which is keyless. So this is public, no keys here. And then we add the second message part. We again have this permutation. We add the third message part. We again have this permutation. We add the fourth message part. We again have the permutation. But now instead of adding something, we read it from this branch here. So ignore that there are two branches. Just say that we take some part here of the permutation. We read the value and we output it. For instance, H1. Okay. Then without changing anything here, we just apply this permutation again. And we again read some part of the output of the permutation, which is H2. And now in sponge terms, so this is actually not really a sponge function because it has a fixed size input and a fixed size output, but it's just an example. In sponge terms, we say that this is the absorption phase, so the absorbing, and this here is the squeezing phase. So essentially in the absorbing phase, we basically process the input, we add somehow the input to our function, and in the squeezing phase, we generate the output. Okay, so these are two terms for sponge functions, absorbing and squeezing. And now I've told you that basically we have two branches. We have the first branch here, where we basically add something and then we read something. And then we have the second part here below that we basically don't touch ever. And this is also due to the sponge construction. Essentially, these two parts are called rate and capacity. So the first part here is the rate. We call it rate in sponge terms, so also outer part sometimes. And below is the capacity, which is called the inner part originally. And normally we say that the rate is R and the capacity is C, and generally, so usually R and C give the number of bits we reserve for the rate part for a permutation size, and the number of bits we reserve for the capacity part. So just as example, for example, if we have a 128-bit permutation, so for instance, IS with a known key, then we can, for example, reserve 64 bits here, so that, for example, the least significant 64 bits for the rate part and the most significant 64 bits for the capacity. But this is just an example, of course, don't use it this way, just as an example. Okay, what you can say that is basically this part here above, the rate part, processes the input and also produces the output, and the part here below, the capacity, is untouched. And now you may ask, well, why do we even need the capacity part? Because essentially, if we only use the rate part for the input and also for the output, and we don't do anything here, why do we need that? And actually, intuitively, well, if we don't use that, then using H2 or only H1, so one of them doesn't really matter. So if this were the whole permutation part here, the rate part, then what we could do essentially is we could compute back here. So it would be possible to essentially compute backwards, because P is permutation. So we can compute the input given the output, but only given the whole output. And now this is just a hint here that essentially the capacity omits this, so avoids this problem, because essentially we never give the whole output to an attacker. But this is only part of the security. And we won't go into details here, but just as an intuition. So there's the absorbing phase and the squeezing phase, and there's the rate part and the capacity part in the sponge function. And what can we say about these two parts? Well, the rate determines the performance of the sponge function. Because of course, if we increase the rate, then we have a higher throughput, because basically we can process more bits for each permutation call. However, if we have the capacity, so the capacity determines the security of the sponge function. So if we essentially increase the capacity part, so if we have more bits there where we don't do anything, we increase the security. So what this means is that if we have a fixed permutation size of, for instance, 320 bits, then essentially increasing the rate decreases the capacity and vice versa. So we have some trade-off between performance and security in a sponge for a fixed permutation size. Okay, but this is only a hash function, right? So, and it's actually not really a hash function, because it's a fixed size input and a fixed size output, and that's usually, so maybe a fixed size output we can live with that, but with fixed size input it's not really nice for a hash function. So what we would do, this is only for illustration now, and maybe we'll change the slide because it's not really correct now. But essentially what we would do is, if we had more message parts, then we would just add more of these steps here. So more permutation calls, more addings of the message parts, and at the end we would generate some outputs. And the number of outputs we generate here is basically depends on the size of the hash value we want to have. Okay, but this is just an example. Okay, still this is without any keys, but we talked about keys before. And catchup is actually not the hash function. So this is the hash, for example, catchup. We'll come to that also later. But yeah, so we talked about keys. And the nice thing about these sponges is, and this is maybe the nicest thing of all of them, is that it's very, very easy to modify for nearly everything you can think of, at least cryptographically. So for example, if you want to build a MAC, so a MAC is a message authentication code. It's similar to a hash, but not quite, because it also takes a key as an input, and it also has to fulfill different security properties. But essentially what a MAC does, it authenticates an input. Okay, it gives you a tag value which authenticates the input. It doesn't encrypt or decrypt, it just authenticates the input. And now if we want to build a MAC using this sponge function, it's very easy because, for example, we can use it such that before absorbing the message parts, we just absorb the key parts. So this is one variant, and I think there's also a variant where you start with the key in the beginning of this initial state, and then you start absorbing the message parts. So there are many variants which allow us to build a MAC, and this can actually all be shown, so proven, to be secure, provided always, of course, that this permutation P is a good permutation. Okay, so this is a first example. We can easily modify it to achieve a MAC function, but also for a cipher, for example, we can output the ciphertext blocks right after absorbing the message. And this is called duplex sponging, and something which is based on that is, for example, used in ASCON. We'll see it in a minute. And for all that, so for most of that actually, for all these variants and use cases, the only thing we need is a good permutation in the middle P. And a good choice, of course, for the rate and capacity. So this is very easy. Choosing the rate and the capacity is usually very easy. We just adapt it to our use case, whether we need a very large throughput or a higher security. But yeah, the more complicated thing is potentially to choose the good permutation P. But if we have this good permutation, then we can essentially build nearly anything with this sponge function. So that's the very nice thing about that. Okay, let's see an example, a concrete example. So for example, is this ASCON scheme, and this was actually developed on this institute. And this is an AAD scheme, which means that essentially it encrypts some plain text, but it also provides authenticity of that, and also of some associated data blocks which are not encrypted. And what this does, so this is essentially the whole ASCON function here in encryption mode. And we essentially have a sponge function with, again, different permutations. So this is actually the same permutation, I think, but with different numbers of rounds. And we have some details here, but essentially here's the duplex effect here. So we have, for example, we add one plaintext block and we squeeze one ciphertext block, and we do this in each step. But in a sense, what is the important thing here is that essentially we have a sponge function which, given this permutation here, can be used to build a whole AEAD scheme. So not only a hash function, not only plain encryption, not only a MAC function, but essentially all of that together. And all of that from this single permutation. Which means that if we basically use a different permutation here, which is equally strong, that we wouldn't necessarily decrease the security. Maybe the performance, because it's not so good anymore, maybe, but not the security, essentially. Okay. So what we can have with the sponge function is actually provable security levels, which is a very nice thing. We can also have this with some modes, but not with a block cipher alone, for example. So a sponge function provides provable security levels, of course, always assuming that the permutation we use in the middle is actually a good permutation. So that's the thing we need to make sure as a designer, and this can't be proven, unfortunately. But if we assume that, at least we don't know how, but if we assume that, then essentially the sponge can be proven to provide some security. And roughly speaking, the security is C, so the number of bits we reserve for the capacity part, divided by 2. And this is now, for example, reasons like the birthday attack. We won't go into the details here, but roughly speaking, that's the security in bits a sponge function gives you. So if, for example, if you use a capacity part of 16 bits, then you won't have a very large security. Okay, but of course there are also other factors. So for example, if we produce, of course, a hash value, so these are these H1, H2 values from before, then of course the security also depends on the size of this produced output. And with all of that, the focus of a new design using a sponge function becomes the permutation, this calligraphic P, because this needs to provide some properties in order to basically use these properties of the sponge. Okay, we can build many variants with the sponge function. So there's the very simple sponge function for a hash function. So for example, SHA-3. And there are duplex-based constructions which alternate absorbing and squeezing. Or, well, maybe alternate is not the right term. Maybe you can also say they do it simultaneously. It depends how you define it. Then there are things called outer keyed sponges. So we basically they can be used for max, for example, where we add the key in the rate part before adding the message parts. And there are even variants with full state absorption. So instead of having a separated rate part and capacity part in this absorbing step, we just absorb into the full state. And for all of these constructions, there actually are security proofs also available. And sponges are quite popular recently because they're so nice and so versatile. So many new proposals for lightweight constructions are actually based on these sponges. So there are also other properties. For example, usually we try to use larger permutations. So for the sponge, because if we have a permutation of a size 128 bits, for example, even if we use only 2 bits for the rate and 126 bits for the capacity, we can only reach a security of around 63 bits due to this limitation of C-half. So usually in a sponge function we have larger permutation sizes. So this may have negative impact on some implementations, but usually it should work fine still. Okay, so as an example, and this is just a permutation now, and I think it's also included in the exercise sheet of next exercise, if I'm not mistaken. But what we have is this catch-up permutation, which essentially has 1600 bits. And inside a sponge function, this catch-up permutation is essentially this math call P, where we essentially call it again and again. And in the middle, we always absorb either a message part, for example, or we produce some output. But that's the difference essentially between the permutation which is used and the whole sponge function, which uses this permutation internally. Okay, so it's a small summary. So the idea of not the main idea, but a nice property is that we essentially reduce the number of operations which involve the secret key. Essentially, we normally have it only in the beginning and then at the end, not anymore, if we have some keyed construction. It's also a very versatile construction, so there are a lot of things we can do with that. We can build a MEC function. We can also build some encryption function, so a cipher. So it's very versatile. And the main focus of the analysis is then usually the internal permutation. So if we try to have a new design using a sponge function, we, as designers, we usually focus on the analysis of the permutation we want to use the sponge with. Because this decides, of course, so how good the permutation is decides, so it needs to be good for the security of the sponge, but then we also try to build it in such a way that the whole operation becomes more efficient in some use cases. Yes, so the sponge function provides provable levels of security, always assuming, of course, that our permutation is a good one. And there's this trade-off between the rate, the throughput, or the performance, and the capacity, which basically determines the security in part of the sponge function. And yeah, the standard model consists of 2 phases, so you basically have the absorbing at the beginning and the squeezing at the end. But again, this is not true for every sponge function. This is just for the standard model, for the basic model. Okay, thank you very much. So maybe I'll update the questions later because I have only a single question about sponge functions, which is not very creative, but yeah, maybe I'll update that. So yeah, keep a look at the website before the exam maybe. But yeah, other than that, it should be that. Yeah, so thanks for attendance. If you have any questions, just ask them. I will be here for a couple of minutes still. And of course, also if we have some questions about the previous part about stream ciphers, don't hesitate to ask. Thanks.